Hey there, everybody. Welcome back. We've got one last video in our curvature section for vectors. This is 12.5. We got some examples. This is Calc 3, Anton 11th edition, fall 2022. Let's just jump right into it. I've got a little piece of extra information for you. I'm not going to test you on it. It's just kind of cool to think about what happens with curvature when we don't have vectors. So if we have y equals f of x in our regular 2 dimensions, 2 space, kappa of x is the magnitude of y double prime divided by 1 plus the quantity y prime squared. You take that to the 3 halves, which is effectively the magnitude of f double prime divided by 1 plus f prime of x squared to the 3 halves. We're not going to do anything with it. This is just some extra information for you to have in case you want to play around with it. Let's just take a look at the vector r of t equals 5 cosine t for the x component and 2 sine t for the y component. This ends up being the ellipse x squared over 25 plus y squared over 4 equals 1. Okay, so let's take a look at what happens here. Let's find our curvature and see how this compares with the circles. So I would take the derivative. We'll use 0 to 2 pi for t time to get that full ellipse. So we got r prime is -5 sine t, 2 cosine t. And we'll, of course, take the magnitude of that. We get 25 sine squared t plus 4 cosine squared t in the radical. Nothing cancels out as is. So what we're going to do is we're going to break off this 25 into 2 parts. We're going to write it as 21 sine squared t plus 4 sine squared t. That way it allows us to put these two make that, but now I could put these two together and make that a 4. It just makes it a little bit cleaner, not a whole lot, but that's what we're going to use. So our magnitude of r prime is square root of 21 sine squared plus 4. Let's take a look at r double prime. We've got -5 cosine t, -2 sine t. I chose to do r prime cross r double prime for kappa here because 2 space, when we convert it to 3, we get some 0 components to k. And that makes the cross product really easy. If I do r prime cross r double prime, the I component zeroes out, the j component zeroes out. All we're left with k is 10 sine squared t plus 10 cosine squared t. So we factor out the 10 and sine squared plus cosine squared again is 1. We've got 0, 0, 10 is the r prime cross r double prime. And we want the magnitude of that, and the magnitude of something that's got 2 zeros is really easy. It's just itself. Check it out. Give it a try if you need to see it. But we have kappa of t is that magnitude of that last component right there, divided by r prime cubed, the magnitude of r prime cubed. We've got magnitude of r prime right here. So we cube it, and since there was a square root, we're going to write it as to the 3 halves. This is kappa of t. Let's take a look at what happens at little individual components of time. So when I let time equal 0, we get the curvature is 4/5, or the radius of curvature would be, I'm sorry, 5/4, or the radius of curvature would be 4/5. I'm going to do that with t equals pi over 2 as well. We'll check it out along the y-axis. When we do that, this is no longer 0. This is 1, so we've got 21 plus 4 is 25. We've got 5 to the 3 halves, or 25 to the 3 halves is 25 times 5 is 125. So we had 10 on top, 125 on bottom. This ends up being 2 over 25. So the radius there would be 25 over 2. Okay. Now, before I show you the Desmos version, I'm going to show you what I attempted to do by hand. So I graphed, well, actually, maybe I'll show you the Desmos first. I graphed that equation, the y squared over 4 and x squared over 25. And then I showed what happens if I put a circle that has a tangent at the same point here. So if I do a circle that has a tangent at the same point here, with the curvature going the same direction, that's this one right here. And look at that. Kind of neat. And now if I do, that was t equals 0. If I do t equals pi over 2, 25 over 2 was 12.5. So that's my r squared right there. This is 0.4, 0.8 is 4/5 squared. This one, I turn this one on. This is at t equals pi over 2. And we're looking at how the curvature looks right there. Look at that. Tangent line looks the same. So I was kind of trying to show that here. My red circle is a little lame. And I didn't use graph paper, so it was a little bad. But I did t equals pi over 2 for the red circle. The blue circle right here is t equals 0. Just graphing what I knew. This is on Desmos. I think I have that right. dVuj, let's go look at it. dVujwu UADT. That's what I have on my paper. So if you want to look that up, it's a saved graph on my account. That should take you to it. Where's all this going? In general, if a curve C in 2 space has kappa that's not equal to 0 at point P, then there's a circle with the radius of rho equals 1 over k that shares a common tangent with the curve at P. So that's why we call rho the radius of curvature. And it's 1 over kappa. That's what I used in these equations. And we can see that it makes a radius. I got 4/5 squared, which is 5/4 upside down, the reciprocal. This was 2 over 25. The reciprocal is 25 over 2, which is 12.5. And we can see those both right here. So the curvature at any point for any curve, we can overlap with a curve or overlap with a circle with the radius of 1 over kappa. Whatever kappa is along any curve, if we have the right equation, we can overlap a circle with the same radius that has the same exact tangent. Notice I had to figure out the centers here. Like I had to go, I used the 0.8, I went 0.8 backwards from 5. So 0.8 backwards from 5 gave me 4.2 as the center. That's how I got x minus 4.2. The same thing happened with this. The value up here was 0.2. I needed my radius to be 12.5. So I subtracted 12.5 from 2, and I got 10.5, negative 10.5 as the center of the circle. For along the y-axis, the x was already done there. There is a little bit more we can interpret this as. Let me bring my viewer back up. So there's another 2-space interpretation. If we treat tangent as cosine of phi, sine of phi, and that makes d10, the derivative of the tangent with respect to phi, negative sine phi, cosine phi. So what does that look like? Let's take a look at a picture. I've got some curve T, or some curve C, the tangent line T. Phi is the angle with the x-axis, okay? So if T equals cosine phi, sine phi, then dt is negative sine phi, cosine phi. If we want to write dt ds, remember kappa is the magnitude of dt ds. We can rewrite it by splitting it into dt d phi and d phi ds. So we take the norm of that. This is still the norm of dt d phi. D phi ds is a constant, so we're just looking at the absolute value when we take the norm of it, because it gets squared when we take the square root of it. But if we look at the magnitude of dt d phi, we've got negative sine phi and we square it, and we got cosine phi and we square it. That's going to give us sine squared plus cosine squared, right? That's just going to go to 1. And all we have left is the absolute value of d phi ds. So kappa equals d phi ds in this case. So what does that really mean? The curvature in 2 space is the magnitude, absolute value and magnitude of the rate of change of phi with respect to s. So it's how much theta is changing with arc length as we travel along s. So if d phi ds equals 0, then it's not changing. We have a straight line. And if d phi ds is strong, the larger d phi ds is, the greater this curvature is, because it means the angle is opening up wider even faster. As we travel along, the angle opens up wide really fast. That'll be it for 12.5. Peace.